The idea is that they're pulling answers from different universes simultaneously. They don't even completely understand how this is working, but the amount of power in computing is incomprehensible, and it's probably the biggest breakthrough technologically in human history by a long stretch. And it's all happening without most people even being aware of what the implications are. What if every calculation you've ever made happened not in one universe but in many? Could solving the impossible mean tapping into worlds we can't even see? Google's Willow chip has taken the world of quantum computing to new heights, leaving scientists questioning not only the boundaries of technology but the very nature of reality. This revolutionary quantum processor achieves something truly extraordinary, solving a complex problem in under 5 minutes, a task so difficult that even the fastest supercomputers on Earth would need an estimated 10 septillion years to complete it. Yes, that's 10 with 25 zeros behind it. What's more, some researchers suggest that this breathtaking computational power might hint at a connection to parallel universes where calculations could be happening across multiple realities at once. In this breakdown, we'll explore Willow's historic achievement, the multiverse hypothesis that sparked so much debate, and why some experts remain skeptical about the broader implications. To fully appreciate Willow's accomplishment, it's essential to understand the basic difference between classical and quantum computing. Classical computers process information using bits, which exist in one of two states, 0 or 1. Quantum computers, on the other hand, utilize quantum bits or qubits that harness the principles of quantum mechanics. Qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. Additionally, qubits can be entangled, a phenomenon where the state of one qubit is instantaneously linked to another, no matter how far apart they are. These unique properties allow quantum computers to process an astronomical number of possibilities at once, something classical systems simply cannot replicate. What makes Willow's achievement so groundbreaking is the specific problem it solved. The chip was tasked with generating outputs for a random distribution benchmark, which involved navigating incredibly complex and entangled quantum patterns. For classical computers, this task would have been effectively impossible, taking an unfathomable amount of time. Willow, however, completed it in under 5 minutes. This demonstration of speed and efficiency marks a milestone in what scientists call quantum supremacy, the point where a quantum computer outperforms even the most advanced classical systems. This isn't Google's first quantum supremacy claim. Back in 2019, the company unveiled a 50-qubit chip that solved a computational problem in 200 seconds, a task Google argued would take classical supercomputers 10,000 years. IBM later challenged that assertion, suggesting the problem could be solved classically in days rather than millennia. But Willow, with its 105 qubits, represents a quantum leap forward, quite literally. Each additional qubit doubles the computational power of a quantum processor, so Willow isn't just marginally better than its predecessor, it's exponentially more powerful. Adding to the significance of Willow's success are its cutting-edge error correction techniques. Quantum systems are notoriously fragile, with even the slightest environmental disturbance causing computational errors. Google's advances in stabilizing qubits and improving error correction make Willow not only faster but more reliable, an essential step toward making quantum computers practical for real-world applications. So what does this mean for the future? For now, Willow's achievement is largely theoretical. Solving the random distribution benchmark doesn't have immediate practical applications, but it showcases the transformative potential of quantum computing. In time, machines like Willow could revolutionize fields such as cryptography, drug discovery, material science, and climate modeling. The possibilities are vast, and this milestone offers a tantalizing glimpse of what's to come. But there's another layer to Willow's achievement that has captured the imagination of scientists and philosophers alike: the possibility of parallel universes. This idea, which sounds like science fiction, is rooted in serious physics, specifically the multiverse hypothesis. Quantum mechanics tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. However, when these particles are measured, they appear to collapse into a single state. This is the foundation of the Copenhagen interpretation, the most widely accepted explanation of quantum mechanics. But what if those other states don't actually disappear? Physicist David Deutsch, a pioneer of quantum theory, proposed the many-worlds interpretation, which suggests that every possible outcome of a quantum event exists in its own parallel universe. For example, if you flip a coin, it might land heads in one universe and tails in another. Scaling this up to a quantum computer like Willow, the hypothesis suggests that when it performs a calculation, it might be exploring different solutions simultaneously across countless parallel universes. The final answer, then, would emerge in our universe as the product of collaboration across infinite realities. It's a mind-bending concept that, if true, could offer a profound explanation for the seemingly magical speed of quantum computation. Of course, not everyone buys into the multiverse theory. Many physicists favor the Copenhagen interpretation, which sees quantum states as probabilities that collapse into a single outcome when observed. No need to invoke parallel worlds. Whether Willow is tapping into alternate realities or simply exploiting the extraordinary properties of quantum mechanics, its performance is undeniably impressive. Still, skepticism remains. Critics have pointed out that Willow's achievement, while remarkable, involved solving a theoretical problem with no immediate real-world utility. Physicist Sabine Hossenfelder, among others, has likened this to building the fastest race car and testing it on an empty track. Exciting but not yet transformative. There's also the issue of scalability. While 105 qubits represent a significant leap forward, practical quantum computing will require millions of qubits working reliably and without errors. Despite Google's progress in error correction, the field still has a long way to go. None of this diminishes the importance of Willow's achievement. Each milestone, however theoretical, brings us closer to a future where quantum computers could solve problems beyond our current comprehension. From faster drug discovery to breakthroughs in material science and ultra-secure encryption, the possibilities are staggering. Willow is a step forward, a testament to the power of human ingenuity, and a glimpse of what lies ahead. Quantum computers are still in the early stages of development, but they operate based on principles of quantum mechanics, which is a theory that governs the behavior of particles at very small scales. One of the most intriguing aspects of quantum mechanics is the idea of superposition, where quantum bits, qubits, can exist in multiple states simultaneously, and entanglement, where the states of qubits can become linked in such a way that the state of one qubit can affect the state of another, even at a distance. The idea of tapping into parallel universes comes from a concept in quantum mechanics known as the many-worlds interpretation, MWI, which suggests that every quantum event can lead to multiple possible outcomes, each occurring in a separate branch of the universe. According to MWI, every time a quantum measurement is made, the universe splits, creating parallel versions of reality where each outcome happens. However, quantum computers themselves don't directly allow us to access parallel universes in the literal sense. They leverage quantum phenomena like superposition and entanglement to perform computations that would be infeasible for classical computers, but they don't imply that we can interact with alternate realities. The idea of parallel universes is more a philosophical or theoretical extension of quantum mechanics rather than something directly achievable with current or foreseeable quantum computing technology. While the direct connection between quantum computing and parallel universes remains speculative, the ability of quantum computers to handle complex calculations involving probabilities and superpositions brings us closer to testing some of the foundational ideas of quantum mechanics. So, are quantum computers like Willow tapping into parallel worlds, or is their power simply a reflection of advanced probability manipulation? The truth is we don't know yet. But as we continue to explore the mysteries of quantum mechanics, one thing is certain: the journey will be as fascinating as the discoveries themselves.